All right, I want to go over a couple of these questions. So, first one here with this is in the solving equation with rational exponent section. This here, there's a couple different ways we can view this one, but I think the best way is to it's a radical equation. It's got a root in it, so let's just isolate that root. So I'm going to add 5 root x to both sides. So we get x plus 6 is equal to 5 root x. Now, a lot of times I like to isolate the x, but you can divide both sides by 5 if you want to. But you don't necessarily need to. As long as it's completely multiplication here, you can actually have that number up front. So what I'm going to do is I'm just going to square both sides, try to get rid of that square root. So I'm going to square this side, and we will square this side. So x plus 6 squared, remember yesterday we talked about that, that's x squared plus 12x plus 36. Okay, that's x plus 6 times x plus 6, so you have to FOIL that. And then this here is 5 radical x times 5 radical x. Well, 5 radical x times 5 radical x. That's 5 times 5, which is 25. And then radical x times radical x is just x. So now we'll have x squared. I'm going to move my 25x's over, so it gives me negative 13x plus 36 is equal to 0. That's going to factor to x minus 9 and x minus 4. So then x is equal to 9 and x is equal to 4. I'm just going to plug back in to see if these answers work. So we get 9 minus 5 root 9 plus 6 is equal to 0. Well, that's 9 minus 15 plus 6. Does that equal 0? And it does. So that one works. It's a solution. Then we'll try 4. So I'll go 4 minus 5 root 4, which is just 2, plus 6 is equal to 0. So 4 minus 10 plus 6 is equal to 0. And it does. So both those two solutions work. And I guess that's how you would approach that one. Going now down to this one, this is example 4. This is similar to, I think these questions down here, this is the way I would approach it. But maybe in this section, because of the exponents that we can write here, we can write this thing as x, square root of x, remember, is the same thing as x to the 1/2. The fourth root of x is the same thing as x to the 1/4, and then minus 4 is equal to 0. Remember in class we talked about x to the m over n is equal to the nth root of x to the m. And that's a two-way street. You can start with this stuff like we did in this equation and go to the exponent, the rational exponent format, or you can start with the rational exponent and go to the root format. Either one's fine. But we recognize that this number here is half of that number there. So this thing is in quadratic form. So what I would do, remember, when it is in quadratic form, you just let u be that variable term. Okay, you don't need the coefficient. You don't want the coefficient, but you just x to the 1/4. So we'll let u equal x to the 1/4. And then if I square that, square u, and then square x to the 1/4, it will look something like this. Well, x to the 1/4 squared is the same thing as x to the 1/2. So that's nice because this thing here can be rewritten now as u squared. This thing here is now minus 3 times my u, which was x to the 1/4, minus 4, then is equal to 0. Now, solving this, we can factor u minus 4, u plus 1. And this gives me u to be 4 and u to be negative 1. I remember what u was. It was x to the 1/4. So x to the 1/4 is equal to 4, and x to the 1/4 is equal to negative 1. At this stage, you get some options. Maybe you want to use this thing to go back to this x to the 1/4 being the fourth root of x to the first. And it might open your eyes to the fact that to solve for x to the first, we need to raise that to the 4th power, and then raise that to the 4th power. So when I do that, those cancel out, leaving me just x to the first, and a 4 to the 4th is 256. kind of using the same logic over here. Raise this to the 4th power. Raise that to the 4th power. I get x to be 1. We always got to check our answers to make sure they make sense. When I plug 1 in, so plugging in the 1, I get root 1 minus 3 times the 4th root of 1 minus 4 is equal to 0. So that's 1 minus 3 times 1 minus 4. Does that equal 0? And no, it does not. Okay, it's going to be, what, 1 minus 3, so it's going to be negative 6. So negative 6 does not equal 0. Then we try 256, and just to save you a little bit of time, 256 does work. You'll get 0 on the left-hand side equals 0 on the right-hand side. All right, this question here is another example of quadratic form. That exponent of 2/3 is half of that exponent of 4/3. So we're going to let u equal x to the 2/3. And therefore, u squared would be x to 2/3 squared. I don't know if I stated this, but the reason that I do this, because 2/3 raised to power, this is a power raised to power, and you multiply those. So 2/3 times 2 is 4/3. So I'm making the argument that I do end up with the x to the 4/3 and x to the 2/3 when I let u equal x to 2/3. So now x to the 4/3, which is that term right there, we're going to substitute that and let it be u squared minus 5. Then we're going to substitute x to 2/3 with u, and then plus 6 is equal to 0. This is going to factor to u minus 2, u minus 3. So it gives me u to be 2 and u to be 3. This one's a little bit different in regards to how we have to solve it, because when we plug back in x to 2/3 is equal to 2 and x to 2/3 is equal to 3, we're going to want to get this to the first power. And there's two ways of doing this. I'm going to maybe use the more obvious approach. I write it that way. X to 2/3 is the same thing as the cube root of x squared. Well, I need to get rid of the cube root, so we'll cube this side, and then you cube that side. So that gives you, that's going to be x squared is equal to 8. And now I want to solve for x to the first. So I take the square root of both sides, and I will get x equal plus or minus square root of 8, which that is simplifying to plus or minus 2 radical 2. So that's the solutions we get there. Okay. Over here, I do the same thing. Now I'm gonna maybe use a different approach instead of how I wrote this, because I want to get x to the first, and what we can do is multiply by the reciprocal. Raise this to the 3/2. That's going to give me, when I multiply a power to a power, I'm going to get 6/6, so that is x to the first. But now I'm going to raise this to the 3/2. So this gives me 3 raised to 3/2, which now, using the property that says x to the m over n is equal to the nth root of x to the m, we could rewrite this as the square root of 3 to the 3rd, which is the square root of 27, which simplifies then, and we should have plus or minus when we take square roots, simplifies to 3 radical 3, square root, or sorry, plus or minus 3 root 3. So either approach that you like, you prefer, you can either do this where you rewrite it as a root equation with a symbol, or you can use this technique here. Either one's fun. Give you options there. Example 4, same concept, except for now, instead of this being a monomial, it's a binomial, but we still see this as the first power, and that's the second power, so they're still in quadratic form. So now we let u equal that object, so we'll let u equal x plus 5. So then if you think about it, u squared would be x plus 5 squared, which is that thing right there. So now we'll go u squared minus 3u minus 10 using substitution. It's going to factor to u minus 5 and u plus 2. So u ends up being 5 and u ends up being negative 2. But remember what u was? It was x plus 5. So let's substitute the x plus 5 back in. And then x will be 0. And then here x will equal negative 7. If you plug both those back in, you get 0 on the left and 0 on the right. And they should be true statements. Coming down here, in class we talked about how if we have some object, some linear object inside the absolute value bars is equal to some constant. The way we solve this is we create two individual equations. We create the equation ax plus b equals c. Then we write the word or, and that means that just means that this is a solution or that's a solution. It doesn't mean I get to choose which one I want to do. I then write ax plus b, the object that's on the inside of the inside the absolute value bars, is equal to now the opposite of c. So once you get your original equation to be in this format, you can apply this rule to create your two equations that are then solvable. So I can't do this right away. I got to isolate the absolute value bars. So I'll subtract 5 from both sides, divide both sides by 3. Now this is in that format, so I can say absolute value bars go away. I get x minus 7 is equal to 3. Write the word or, and then I get x minus 7, the argument on the inside, this expression, equal then to the opposite of c. So this is minus 3. So that rule right there is what created that, and that rule right there is what is creating that. When I solve these are a little bit easier. So also x plus 7, or add 7 to both sides, x equals 10. Add 7 to both sides, x will equal 4. So what happens here, what this means to us is that for the expression x minus 7, for the absolute value expression x minus 7, absolute value means distance away from 0. So this is saying, this work here is saying that when x is 4, it places x minus 7, the absolute value of x minus 7, it places it to the left of 0 by 3 units. Okay, think about plugging 4 in here. You get 4 minus 7. Absolute value of 4 minus 7 would be absolute value of negative 3, which absolute value of negative 3 is 3, and distance always has to be a positive number. When x is 10, it places this x minus 7 expression to the right of 0, 3 units. Plug in 10 here, you get 10 minus 7. Absolute value within 3 is equal to 3. It puts it 3 units to the right. So that's why we get two answers, because distance can be that direction from 0, or it can be that direction from 0. This question's very similar. You're going to isolate the 3 x plus 6 in the absolute value. So subtract, basically what I've done is I've added that to both sides, and I'll subtract the 1 from both sides, so it will give me 3. So isolating that, so now I can take 3x plus 6 is equal to 3, or 3x plus 6 is the opposite of 3. Solve both of these. 3x equals negative 3, x equals negative 1. Here we get x equals 3x equals negative 9, and x equals negative 3. You can plug these things back in as well to check. If I go 4 minus absolute, so if negative 1 is here, so that's going to be a negative 3 plus 6. Does that equal 1? Well, that's 4 minus the absolute value of 3. Well, that's 4 minus 3. Does 4 minus 3 equal 1? Yes, it does, so that is a solution. And then we'll try when x equals negative 3, so I'd go 4 minus 3 times negative 3 is 9, or negative 9, sorry, plus then my 6. Does that equal 1? Well, that's saying 4 minus negative 9 plus 6 is negative 3. Does that equal 1? Well, 4 minus absolute value of negative 3. Absolute value of negative 3 is just 3. Is that a true statement? Yes, it is. So that's a true answer.
Close this door. Look at the disruption.
Alright, so we've got absolute value of x minus 1 equals absolute value of 3x plus 2. Kind of explain why we're going to do what we do here. The general rule is simply, if I've got some expression x plus b in absolute value bars is equal to the absolute value of cx plus d. They're both linear. What this is saying is this object here, ax plus b and cx plus d, they could be this. When I know what x is, or obviously this is just a number and that's just a number. They could be in fact the same number. Okay, and that would give me a true statement. For instance, if they were both, I plug in x for both those and I get absolute value of 3 equals absolute value of 3. Well, that would be 3 is equal to 3, true statement. Okay, or they could be opposites of one another. Okay, so I could say ax plus b is equal to the opposite of cx plus d. That idea is plug in x for here, maybe you get 3 back, but plug in an x value here, the same x value, and maybe you get now negative 3 back. But since they're both an absolute value, 3, the absolute value of 3 is 3, the absolute value of negative 3 is still 3, a true statement. So these expressions could be equal to one another, or they could be opposites to one another. So that's kind of what we're going to do here. The negative here, I always put it on the right hand side. You could put the opposite of ax plus b is equal to cx plus d and solve that, and you get the same results. But I always put the negative on the right hand side one. So doing this, we can go ahead and say this rule here. Okay, so that's just taking the absolute value bars away and giving ourselves x minus 1 equals 3x plus 2. Solve that for x. Subtract x from both sides, get 2x. Subtract 2 from both sides, get negative 3. So we get negative 3 halves is equal to x. Now I need the or part, and we're going to write that. So that's just saying take the ax plus b, take the left-hand side, take the absolute value bars away, and just x minus 1. Now I'm going to take the right-hand side, I'm going to take the expression on the inside, 3x plus 2, and I'm going to negate it. I'm going to make it its opposite. And that there matches that there. Now this, and then it's key that you make sure you put this in parentheses because you want to subtract the whole thing. So minus 3x minus 2. Now I can solve for x, so I get 4x, add 1 to both sides, I get negative 1, and so x now is negative 1/4. Now let's see why this works. If I plug negative 3 halves in, okay, I'm going to get negative 3 halves minus 1 is equal to negative 3 halves, right this way, 3 times negative 3 halves plus 2. Well, negative 3 halves minus 1, that is negative 5/4. Sorry, not 5/4. It's just negative 2 or 2. So it gets 5 halves. And then when I do this one, I get, that's negative 9 halves. Plus then 2 is the same as 4 halves. So I get that. Well, negative 9 halves plus 4 halves is negative 5 halves. So we get a situation where they're both the same object on the inside, and the absolute value then of the same object is going to be 5 halves equals 5 halves. And that was the idea where if we've got, I think the example that I used initially was like absolute value of 3 is equal to absolute value of 3. They're the same number on the inside, so when I take the absolute value, the results are the same. But again, they could be opposite, so let's see what happens when we try this negative 1/4 in here. If I go negative 1/4 minus 1 is equal to 3 times negative 1/4 plus 2. Well, negative 1/4 minus 1 is negative 5/4. And now here, it's going to be negative 3/4 plus 2, it could be written as 8/4. So negative 3/4 plus 8/4 is a positive 5/4. Here you see that objects on the inside, the ax plus b and the cx plus d, are actually opposites of one another. but the absolute value of negative 5/4 is 5/4, and the absolute value of 5/4 is 5/4. So that ends up being a true statement. And that's why negative 1/4 is also an answer. Something we always like to do with absolute value is try to catch people off guard with the definition, understand the definition, and we apply the definition when we have the absolute value bars isolated. So I'm going to isolate these absolute value bars and I get negative 15. What we're saying here is that the absolute value of some number, because when x minus 5 is evaluated, let's say x is 20, I'd have 20 minus 5, and it's saying is equal to negative 15. Well, absolute value of 15, that's 20 minus 5, does that ever equal negative 15? Well, we know absolute value is always going to turn something into a distance away from 0, so distance has to be positive. So absolute value of 15 is always positive 15. It can never be negative 15, so this is not a true statement. So that logic says whenever I have an expression, an absolute value expression, isolated, and it says it's equal to a negative number, that's no solution. Absolute value is never negative, can never be negative. So what happens here is that we try, I don't say we won't try, but the logic behind giving a question like this is for people to kind of be robotic about their processes and say, okay, I want to isolate this, I'm going to solve x minus 5 equals negative 15, and I'm going to go x minus 5 equals positive 15, solve both those. You just go through the process, and without any thought, you incorrectly answer the question. This is never going to happen. Okay? You can never have absolute value to be negative.